has taken the kind of ideas I was talking about when I was talking about monad transformers and the way in which we layer one effect on top of another. And one way you can see that what's happening when when you have one monad and then you build another monad on top of it by applying a monad transformer, is that there's a translation being defined from the language with the complicated effect into the language with the simpler effect. You're showing how the new effects that you just added can be expressed in terms of what you had before. So Andre had the idea that what you really ought to be able to do is invert this process and understand that really you've got two programming languages, one with the complicated effect and one with the simple effect, and you really ought to be able to be explicit about the places where you move from one to the other and back again. So he introduces operations of reification and reflection. So here, these two rules, he's got these constructs mu and square brackets. Here we have a value in our programming language. So we imagine we've got a programming language which has already got some notion of effect, and T of A is the explicit representation of an effect modeled by the monad T as a data structure in that programming language. And this I guess, reflection operator lets you take that computation and push the notion of the effects which are explicit here in this is T as data down into the computational level of the language which has a more complicated monad under the hood. So you can take something where you have an explicit data type and you can say this effect I wish to push under the hood and not see anymore. Likewise, when you've got some effectful computation E, so which as far as you're concerned just looks like it has type alpha but is secretly going to have some side effect, then you can reify the side effects of that expression E by applying this square bracket thing, and then you end up with an explicit piece of data in your hands of type T of A, which you can manipulate just because T is an ordinary data type in your language. So I want to show that delimited control is a universal effect for doing this sort of thing. So if your underlying effect is delimited control, then you can perform this reification and reflection for any monad that is definable within the language, not for any monad at all. Obviously, if you've got some complicated effect under the hood, like true concurrency or something, you're not going to be able to reify or reflect that. But if the monad that you're talking about is one that you can define in your programming language, you can define its eta and you can define its bind, then you can implement these reification and reflection operators. And more amazingly, if you've got call CC and a reference cell, then you can encode delimited control. And in standard ML of New Jersey, for example, you do have that combination. And so you can actually implement this reification and reflection operation. And this leads to some truly magical possibilities. So there's a piece of code down here from something I wrote a while ago. So here's a function, app twice. So this is a trivial example of something that's higher order enough to see the effect. And so here I've defined app twice to be do F1, then do F2, and then do done. And ML thinks this has type int to unit to string. Okay? But secretly, ML has a big complicated effect under the hood, right? So we know this is int to T of unit to T of string, really, in ML. It's the implicit T. But by using these reification and reflection operators, we can make that implicit T explicit. So I can apply this function, translate, and then this is a cunningly built combinator, int to unit to string, to app twice, and I get back translated app twice, which is in ML of type int to T unit to T string, which is actually an explicit thing for whatever T was, and I can manipulate it. And this correctly captures the way that the unit and bind of the monad get stuck in the sequencing of these computations. So you can move very smoothly between the explicit and the implicit representation of your monadic effects. And I think this is not sufficiently well publicized, because people often complain that monads mean that your program is infected with monads all over the place, and it's not true if you have this kind of operation. You can push the monads under the hood when you don't want them, and then pull them back up when you want to analyze them and do something clever with them. Okay, so a lot of the bits of work that I've talked about before and that I'm going to talk about next involve circularity. So we have recursive programs and we have recursive types. And when we come to build our models, we'll have recursively defined logical relations. We'll have logical relations which are parameterized by worlds, which are themselves recursively defined. And there are lots of approaches to this. And of course, The most obvious one is traditional domain theory, and lots of people have been using that in reasoning about effectful languages. But more recently, people have been doing similar constructions for those that people have done in traditional domain theory, but over an operational semantics. So one of the most influential ideas that I guess you'll also hear some more about later on in this summer school is that of step indexing. So here the idea is that we're going to build predicates and relations over an operational semantics, and they're recursively defined, and the clever way of breaking that circularity is instead of just defining them in one go, we'll define indexed versions of those predicates or relations, and we'll index them by the number of computation steps that you have available to, I guess, show that something is not in the predicate or not in the relation. And by using this, you can break the circularity very often, because you discover that the definition of your predicate at n steps only depends upon on itself recursively at fewer steps, and that lets you make these definitions. And this kind of idea has been generalized slightly by Lars Birkedahl and his co-authors recently. So he's taken the further move to work with ultrametric spaces, and then further still to something called the topos of trees. An ultrametric space is like a metric space, but it satisfies a strong version of the triangle inequality. So the distance from here to here is less than or equal to the maximum of the distance from here to here and here to here, instead of the sum. And this allows you to solve recursively defined equations by using Banach's fixed point theorem, if you can show that the thing you're trying to find the fixed point of is contractive. And associated with these kinds of things, there are a whole bunch of interesting modalities for defining when things are contractive, and hence when your recursive definition is well founded. So a lot of the logics for reasoning about these things and languages in which we express our predicates and relations now involve a modality of some sort which expresses at the next time. So along that line, the talk I gave about modeling the language with dynamic allocation, I was fixing my store to be first order. It contained integers, and it contained pointers to integers and pointers to integers and things, but it didn't contain any functions, because if you put functions in your store, then suddenly there's a lot more circularity goes around. And you can push what I was talking about forward using domain theoretic ideas, and this is something that Nina Bohr did in her thesis, and in collaboration with Lars Birkedahl. Or you can move, as I was saying, to building models over an operational semantics. So step index crypt key logical relations over an operational semantics. So the idea is that you just take the operational semantics you first thought of, and then you interpret the types of your language as relations over the operational semantics, indexed by some bunch of possible worlds, and indexed by steps to deal with the circularity. So there's been a whole series of papers on these ideas, each of which gets, well, mostly they get more complicated. Sometimes they get simpler as time goes on, but they become more and more powerful, and they can prove more and more contextual equivalences. And in the recent work by Derek Dreyer and Lars Birkedahl and their various collaborators, the possible worlds I was talking about that index these logical relations go beyond talking about invariance. So when I was giving the simple model of the language with dynamic allocation, it was all about invariance. The whole point about the possible worlds was that there was some invariance on the heap that every function in your context was going to respect, and hence you were going to respect them. But it turns out that just thinking about invariance is not enough. We have to move forward to think about variance, a little bit like I was alluding to in the work of Bob Ackey on generalizing monads to parameterized monads. So the possible worlds become themselves little state transition systems. So this work has now got very polished, and one of the more recent papers has a very, very precise and careful analysis of not just here's a model of the language, it works, but a fine analysis of exactly how the model changes if you move between having flat store or higher order store, or if you add or don't add control operators. And you can see exactly what you have to do to the model to make it work for languages with those features. These models contain lots of the sorts of technical devices I've been talking about, including bi-orthogonality. And yes, the most recent ones are in fact fully abstract. And they're not just fully abstract as an academic piece of work, but they're actually practically applicable to verifying equalities that hold between very tricky imperative abstract data types. So something which doesn't get quite so much press as it might do in the Poppy community is game semantics. So game semantics is another style of denotational semantics in which you model types as games and terms as strategies. This has been used in the past to provide fully abstract models for all kinds of programming languages, most famously to give a fully abstract model for PCF. Samson Abramsky and some of his co-authors have applied this sort of 10 years ago or so to models of the new calculus, the pi calculus, and languages with general references. And the models of languages with general references weren't terribly convincing because they didn't actually allow you to compare references for equality, which is one of the central things you can do with a reference in an ML-like language. But Nikos Sevalikos, who's been working in Oxford, recently took their older work on game semantics for references and extended it with nominal structure, the FM structure that I was talking about before. And he's used that to provide fully abstract models of ML-like languages with higher type references. And one of the things I think is very interesting is that this work has been previously slightly on a parallel track to the work on people using logical relations and domain theory and so forth. But in actual fact, the structure of the transition systems that arises in these models is extremely game-like. The transition systems have to be explicit about what transitions are performed by the system and what transitions are performed by the environment. And this is very much in the spirit of game semantics. So I think there's some rapprochement possible in the near future between these two approaches. So there's been a lot of work on compiler correctness, most notably the concert compiler by Xavier Leroy. And some of this work in the last few years has used some of the ideas that I've been talking about. So Andrew Appel and his foundational proof-carrying code project, he worked on, as I guess he's going to tell you later, translating high-level types into a foundational logic. So an idea that the types of your high-level language translate into some predicates over compiled code of that type. And you can use this to prove memory safety for programs in a language with higher types and so forth. And I and some other people have also worked on compositional notions of compiler correctness, both in sense of semantic type soundness, so here showing that the compiled code, so instead of having a predicate like up here, we have a binary relation which expresses a notion of equivalence on the behavior of compiled code. So this gives us a notion of type soundness, which includes memory safety and also adds something about the indifference of the compiled code to, for example, the behavior of the memory allocator. And also on full functional correctness, showing that the compiled code realizes the source program in some compositional sense. So all this work uses, again, these ideas I've been talking about all the way through, bi-orthogonals, separation ideas, logical relations, and step indices. And the work that Derek Dreyer and Gil Herr have done most recently can even verify self-modifying code. They can show that extremely contorted bits of machine code correctly realize nice, well-behaved pieces of functional code from the source language. So, hello. Yes, right. So, if you'll indulge me, this is one of my favorite slides, which I show frequently because I'm particularly proud of it. So this is a piece of cock from one of these bits of work on proving semantic type soundness for a compiler for a functional programming language. And this is a logical relation between values between machine code computations indexed by the types of a high-level language. So we've got integers, booleans, pairs, and functions, and this is the translation of types in this pure functional language into relational Hoare logic assertions on the behavior of the machine code that is supposed to be generated, and the particularly exciting one being, of course, the translation of function types. And I'm not going to take you through all the gory details, but what you can see in here is there's a separating conjunction of relations makes a play. There's some quantification over relations. There's a later operator here. This is one of these modal operators corresponding to the step indices. And there's a perp here. This is the bi-orthogonal constructor, which is the way that we deal with function pointers in the heap. So in all this work, there's a whole bunch of themes that I kind of like to say are important for work in this area. So obviously monads, algebras, and monoidal structure come up all over the place. Bi-orthogonals are coming up in more and more of these bits of work. Separation is everywhere, as are logical relations and parametric logical relations. Recursion and approximation dealt with by all kinds of techniques. this idea that invariants are really important, but everybody is now moving beyond invariants to transition systems of some sort, I think is one that needs to be kind of called out. There's a sense of, there's an interesting interplay between types and logics going on here. We have systems which have both types and logics laid over the top of them. We have systems in which types are explained in terms of logics and so forth. This is an interesting connection to bear in mind. And finally, of course, mechanization is the big story of the last few years. So all this stuff is reaching the point where we're being able to do more and more and more stuff, but the theory is getting more and more complicated. But luckily, we've got Coq around, so we can just about tame the complexity and keep saying true things as we add more sophistication to our models. So I think I will stop there.